I'm recording. All right. Welcome everyone to the platform. My name is Kolani Ndlovu, popularly known as Mr. X, and we are going to do Work, Energy, and Power today. I'm very excited about what's going to happen right now. Work, Energy, and Power. To all those that probably do not have the handouts, I did send the handouts on the WhatsApp groups that I have. I'll put my number towards the end of the lesson so that people can be able to see and know how to get the handouts or whatever further help that they may need. In this platform, you're free to ask anything. So if you're something that you want to ask, something that you don't know, something that I've just done, as I'm going to do many questions here, and you do not understand it, simple raise your hand using the platform. So it's quite simple. All you simply need to do is there's a portion where it says raise hand. Just click onto the raise hand portion, and you should be able to get what you need, or rather should be able to ask all the questions that you may be able to ask or comment or whatever the case could be. Again, another thing that I encourage you guys to do, there is a chat platform on this Zoom thing where you can write your questions as much as I can. I will make sure that I answer them. Otherwise, let's begin our lesson. Here we go. I'm going to just upload this very quickly right there. Then I'm going to stop my video here while I teach in the meantime there. Right, so here's a question that we're going to do together. This question is a 2015 Mpumalanga prelim paper, paper 1, that's it, and it's going to be question number, paper 1, question number 5. Let me just put this at the bottom so that people can be able to see what I'm doing here. Obviously, people will be coming through the platform, so there's going to be a bit of some disturbance here and there, but I'm doing my best to ensure that everyone is within and all. If it so happens that the system kicks you out, or could be your network that kicks you out, please, by all means, try to log in again. Once the maximum number of people has been reached, don't worry, I will upload this on Facebook, on YouTube, on my YouTube channel, Mr. X Mathematics and Science. I think that's for grade 12. Let's start. A windmill on a farm is used to pump stationary water from point A in a well. The water flows past point B, and point B happens to be 335 meters above point A at a speed of 2.1 meters per second. So here's your scenario. You've got point A and point B. Point A is at the bottom, or rather we can say it's underground. The distance from A to B is 35. And then we're told something significant right here. We're told that the water flows past point B, which is 35 meters above point A, at a speed of 2.1 meters per second. So when the water is moving past point B, it is at 2.1 meters per second. 5.1, first question. The first question says, define the term conservative force. So I'm hoping that you guys have your books by the side, write the title of the question as you see it, and then can be able now to start answering together with me. Question says, define the term conservative force. Before we define, in the final examination in a couple of months from now, please note that when it comes to definitions, it's either you're going to get 2 marks or 0. In other words, there is no I know a bit of the definition. I know sometimes parts of the definition. So you must know everything as it were. So we're defining. A conservative force is a force whose work done is path independent. A force whose work done is path independent, right? So that is what you're looking at, what is called a conservative force. Let's keep working. 5.2. So 5.1, a conservative force is a force whose work done is path independent. Write it down. A good example of a conservative force is force of gravity. So if asked for examples of a conservative force, just pick out force of gravity as the nearest, simplest one. 5.2. Calculate the maximum power delivered by the windmill if 87 kgs of water is pumped from the well per minute. That's what the question is asking. calculate the maximum power delivered by the windmill if 87 kgs of water is pumped from the well per minute. So here's what we need to know. From the topic work, energy, and power, work, energy, and power. The power is basically defined as the rate at which work is done. So power is defined as the rate at which work is done. P is equal to W over T, power. But I want you to know that power has another formula. Power is equal to the force acting on the object multiplied by the velocity of the object. When it comes to physics, your choice of the equation will always be affected by the information given. What equation you ultimately choose will be affected by the information that is given. So what do we have? We've got the mass of the water, we've got the time per minute. And please remember that time is measured in seconds. So per minute, that's definitely going to be 60 seconds for us right there. Now we are looking for power. So we can't use the second equation, this one where there's force and this one where there is velocity. We can't use that. We can only use the first one, work over time. We do have time, but let's find out how we can play around with this nicely. So the power, maximum power of the windmill will be equal to the work done over the time taken. Now, what further information do we have? We are given the speed of the water when it flows past point B, 2.1 meters per second. We're given that. As to how do we find the work, because we do have the time, that's okay. So T, we're good. We're still questioning ourselves on work, and ultimately we're looking for power. Now, the formula that you can use depends again on the information given. If you were to go to your formula sheet, you will notice that there's a formula that says work is equal to work done by a non-conservative force over time. So I'll write this like this, then I'll explain it. So there's a formula for finding work done by a non-conservative force as it were. This formula is further broken down to this part. So the work done by a non-conservative force is change in the kinetic energy plus change in the potential energy. That's work done by NC. Again, this will be over time since we're looking for power. The reason why I'm choosing this particular equation is because I have issues to do with mass, 87. I have issues to do with velocity, 2,1. And because of that, because I have issues to do with mass and issues to do with velocity as it were, I should then be able to use this particular formula that says EK plus EP, change in, right there. Now let's break it down even further. Change in kinetic energy. Kinetic energy has a formula, half mv squared. Change in kinetic energy will be the final kinetic energy minus the initial kinetic energy. Change in potential energy, EP, will be the final potential energy minus the initial potential energy. Your choice of the equation is ultimately affected by the information that is given. So here in this case, I'll have a half mv f squared, okay, minus a half mv I squared, that's change in kinetic energy, plus change in potential. The formula for potential energy is mgh. mgh final minus mgh initial. Since we're dealing with power, all this will be over time. The rest is us putting information in. Follow my lead. So we know everything about the velocities, the initial and the final, because this windmill on a farm is used to pump stationary water. So the water was initially stationary, pumped by the windmill, it moved upwards. Fine. So then it's going to be a half, okay? The mass of the object or the mass of the water, 87, multiplied by the velocity final at point B, which is 2,1 squared, half mv squared minus a half mass 87, velocity initial, it was stationary water, 0. You must show this in the exam. Plus, right, now I'm on potential energy. Mass of the object, water 87, G 9,8. Final height, obviously you can see the height from point A to point B is 35. Multiply this by 35 minus, again, mass 87 times 9,8. What was the initial height where the water was taken from? It was 0 right there. All this over the time per minute, which is 60 seconds. We're looking for power. And so because we're looking for power, power is measured in watts. The rest is calculator business. Your answer is now 500,55 watts. That's the answer to this question. I need to make a disclaimer here. I need you guys to understand this. When it comes to work, energy, and power, your choice of the equation, again, is intimately affected by the information given. Your information should be able to tell you or lead you to what kind of equation you will ultimately use. So at the end of the day, the power provided by the windmill in this case is definitely 500,55 watts. Basically, that's it. So you can write this down quickly, trying to look at the messages that people are sending there and all that. Okay, can you please help those that are struggling with audio so that they can be able to pull through? If you're struggling with audio, guys, it's pretty simple. On the left-hand side of your phone device, there should be something that looks like an earphone icon. On that particular part, please do click onto it and say dial over internet, should be able to come through onto the Zoom part. Guys, write this down here and we'll take it up. So you raised up your hand and I want to deal with you right now and then ask to unmute you. Let me just look for you quickly. There you are. I'm asking to unmute you. You can ask.
Hello, sir.
Hi, how are you?
I'm good, and you?
Great.
So I don't understand how you came up. How your answer was 500,5510.
500,555 watts. That's what I said. It's 500,55 watts. Yes, that's what I said.
So I don't like. It's on this thing. It's half times 87 into 2. Is it 2,1?
Yes, that's multiplied by 2,1 squared.
Then you have minus half times 87, 0 squared.
Yes.
Times 8.
And
then you have. Then on the other side, what do you have?
Plus 87 times 9,8 yes. times 35 minus 87 times 9,8 times 0. Then I get 0. The power is 500. You okay?
You did. Okay, yeah, right. I understand it.
Lovely.
Thank you.
So thank you. So can you mute? Yeah, you can mute yourself in the meantime, just to make sure that everything is fine and all. All right, let's keep working, guys. Write this down. I'm giving you the next 30 seconds on all of this. If you're using a phone, because I'm writing on a bigger screen, just try and zoom in. You should be able to see what I've written in total. So you can move the screen of your phone pretty much well and zoom in from there on. All right, guys, I'm taking this out. Let's go to our next question. I want to cover quite a lot of things today. Let me take this out. Work, energy, and power is the topic of concern. Sharp, here we go. I'm on my next part there. I want to make sure that you guys get what I'm saying and all. All right, let's move on to my next question. All right, here's my next question. It's a 2015 Eastern Cape paper. It's a prelim paper, 2015 Eastern Cape, prelim paper 1, and it's question number 5. Please write the title for the question. I did send the handouts on the group. I'll put my number towards the end of the lesson so that if you want to, you can also get this particular handout. 2015 Eastern Cape, prelim paper 1, question 5, and I'm reading in your hearing. During a fire extinguishing operation, a helicopter remains stationary. In other words, it's hovering above a dam while filling a bucket with water. The bucket of mass 80 kilograms is filled with 1,600 kgs of water. It is lifted vertically upwards through a height of 20 meters by a cable at a constant speed, and that's put in capital letters, of 2 meters per second. The tension in the cable is 17,000 newtons. Assume that there are no sideways motion during the lift. Air friction is not to be ignored. That's interesting. Air friction is not to be ignored. So here's our situation. Let's deal with it. Let's understand it. Let's play around with it and see if we can win from that particular aspect. Now, we have a helicopter stationary, filling in water. The bucket has a mass of 80, and then the water that is filled in is 1,600 kilograms. This particular bucket with water of 1,600 kilograms is lifted, right? Is lifted up through a height of 20 meters by a particular cable at a constant speed. I need to get this right. In work, energy, and power, if you hear the words constant speed, constant velocity, what it actually means is that the network on that particular object is zero. So the meaning of constant speed, constant velocity, is that the network is equal to zero. Not just the network, but more importantly, the acceleration is zero. Not just the acceleration, but again, the net force is actually equal to zero. So these are the implications of the phrase constant speed. The phrase constant speed tells me that the network acting on an object is equal to zero. The acceleration on the object is zero. The net force on the object is zero. And the change in the velocity of the object is also zero. Constant speed, constant velocity, these are the implications. You need to get this thing right. You need to make sure that you understand this and get this right. Network zero, acceleration zero, F net zero, change in velocity zero. Listen to my English. I never said that the velocity is zero. No. I said the change in the velocity is zero. Not necessarily the velocity. Its change is zero. That's important. Let's begin our question. Obviously, the first ones are the definitions, and there we go. State the work energy theorem in words. And the answer is the work energy theorem in words states that the network, right? The following, the network done on an object is equal to the change in its kinetic energy. The network done on an object is equal to the change in its kinetic energy. 2 marks in the exam. Please remember, it's either 2 marks or nothing. 5,2, 3 marks. Draw a labeled free body diagram showing all the forces acting on the bucket of water while being lifted upwards. All right? All the forces acting on the bucket of water while being lifted upwards. So the free body diagram is it way. You show it by a simple dot. Free body, you show it by a dot right there. Now, air friction is not to be ignored. So the bucket is moving upwards. That's the direction. That's fine. There is this force acting, one of the most popular forces, force of gravity, or you can call it the weight. That's okay. Then, because the object is moving upwards, When we define friction, whether air friction or friction on a horizontal surface. We define friction as the force that acts opposite to the displacement of the object. Because the object is making its way upwards, the force of friction in essence will be acting downwards. Remember, I'm drawing the free body diagram. So there's this force here, which is acting downwards. Its name is force of friction. There's a cable that is holding the bucket, and it is this cable where we find a very important force acting upwards, allowing the bucket to move upwards. This force is known as tension, the force that exists in cables. The statement even says this to us: the tension in the cable is 17,000 rather newtons as it were. So your free body diagram would look something like that. Basically speaking, force gravity, weight, force friction as it were, and tension. Now, maybe a question that could be hanging in someone's mind is this: does the length of the arrows matter? Now, you need to understand the background of arrows. Forces are shown by arrows. The direction of the force will be shown by the direction of the arrow. In this case, as an example, the tension is an upward force, while force of gravity on the flip side is a downward force, together with friction, air friction to be specific. Okay, not a problem. So somebody is saying, okay, so which one is longer? Should the tension be the longest? Should force of gravity be longest? Should force of friction be longest? Whatever the case could be. When it comes to a topic which I will teach you guys and probably do a lesson with you, maybe online, the topic application to Newton's laws, that's when I'll become more specific on this. Otherwise, in this particular lesson, there is no particular penalties that you will face if you are not to write it in length to say, okay, this one is the longest. So it's okay to write it like this. It's okay. For now, when I teach you the topic, which is application to Newton's law, then from there on, you should be able to get everything that you need from that particular aspect. I'm going further to my next one. That's 5.2. 5.3. Use the work energy theorem, which we defined in 5.1. Use the work energy theorem to calculate the work done by air friction on the bucket of water after moving through the height of 20 meters, 5 marks. I'm beginning to write everything now. Work with me. The work energy theorem says the work net is equal to the change in the kinetic energy. Now, understand with me that from the free body diagram, there are 3 forces acting on the bucket. There's obviously the force of tension. There's obviously the force of gravity. Obviously, again, there is the force friction. We are not looking for the forces. We are looking for the work done. And I think that's key for me. The work done by air friction on the bucket of water. We're looking for the work done by air friction. So pretty much from the free body diagram, the 3 forces are doing work. So there is the work done by the tension, plus the work done by gravity, plus the work done by air friction. Remember, net, the word net means sum of. So I'm adding all the works done by the forces. If you were to start with this topic from theory, you should be able to understand that forces do work. Forces do work. So there is work done by tensional force, work done by gravitational force, work done by air friction force. These works added together give you net work. I was clear in the beginning that since we are moving at constant speed, the net work will be equal to 0. That's what I say. Since we're moving at constant speed, the network amongst a number of things will be equal to 0. So the formula for work is equal to F delta X cos theta. But notice that this formula is very selective. You know why? This formula would be applicable if the objects are moving on a horizontal surface. Hence, you can put delta X, horizontal surface. So then now, this is not a horizontal surface. This is a vertical surface. So then how do I deal with the situation where I have a vertical surface? How do I deal with it? It's the same thing. You can write it as F, all right, this time delta Y, and guess what? Cos theta. Same thing. I just wanted you guys to understand that when it's horizontal, delta X, when it's vertical, delta Y. It makes sense. Look at it. In the Cartesian plane family, in the Cartesian plane, this will be the y-axis, this will be the x-axis. Horizontal, x. Vertical is y as each way. So now I'm looking for the work done by friction, WF. Let me see what I have, right? Let me see what I have. Follow my line of thought. So I do have, or I can get the work done by tension. It will be force tension, all right? Delta Y cos theta. Great. I can get the work done by gravity. It will be force gravity, okay? Fg delta Y cos theta plus work done by friction, which I'm looking for, ultimately is equal to 0. Let's see my numbers. Let me see if they work. Ft, force of tension. I have my information, 17,000. I want to write this down here. 17,000 multiplied by delta Y. I think we're given a number here, 20 meters, upwards 20 meters, right? That's 20 multiplied by cos, and now it gets interesting, cos theta. Now notice that the theta is always the angle between your force and your displacement. If I was to revisit the free body, the tension is moving upwards, or rather acts upwards. And then the object is also moving upwards, delta Y. So tension and object are in the same direction. So the angle theta between them is 0. I want to say that again. The angle theta is the angle between the force and the displacement. If the force and the displacement move in the same direction, then theta is 0. As you can see, plus, I'm now here, force of gravity. Force of gravity has a formula, Fg. It has a formula. The formula is mg. So where there's Fg is mass of the object multiplied by the gravitational acceleration. The mass of the object is 1,600. That's the water. But please don't forget the mass of the bucket, 80. So M is 1,680. G is 9,8. That's mg. Delta Y, how far did we go? We went 20 meters multiplied by, check this out, follow my lead. Remember, the force of gravity from our free body is downwards. And what did we say? We said that if the force and the displacement are in opposite direction, then theta would be 180. So cos 180 plus the work done by friction, all this is equal to 0. Everything else is a number. You get an answer here, you can get an answer here, and you're looking for the work done by friction. And the answer is negative 10,720 joules. That's your answer. For me, it makes so much sense. The work done by friction should be negative. Why should it be negative? Because friction is acting opposite to the displacement from the free body diagram. And again, then, the work done by a force which acts opposite to the displacement, that work done should be negative. Write this down, family. That work done definitely should be negative. You let me know if there are any struggles, any questions, anything that you probably want to ask me. I'm here for you. Just want to make sure that everything is clear. work, energy, and power, 30 more seconds. Write this down. Have confidence when you're doing questions. Read your notes, understand them, and take it up from there. Sean, you got your hand up. I'm going to unmute you. Go ahead. Okay, Sean, I tried to unmute you.
Sir, I wanted.
I can hear you now.
Oh, sir. Yes, sir. If we're having an suspended object, we don't include the sign for FG.
A
Do we
suspended
include
object.
Yes.
All right. So if you have a suspended object, like an object that is attached to maybe a wall, a ceiling, like a light, chandelier and a light, like that.
Yes, sir.
You do.
I've
Force
noticed.
of gravity is still there. You saying?
I meant that the angle in FG, do we disregard it or sign is not there because?
Oh yes,
Yeah, that's
now
what
I
I didn't.
understand. Okay, you disregard it because the object is not on an incline. This is a simple vertical scenario. So the whole idea of mg sine theta, blah, blah, that's a simple, this one is a simple vertical scenario. So you disregard that. It's a simple vertical scenario. Thank you for that question. Now I understand where you're coming from. So I think you were trying to say to me mg sine theta, but again, there's no angle of inclination because this particular bucket water system is not on an incline as it were. I think, Litaba, you asked a question on the chart there that says, so what about the tension force? I didn't catch that. I'm not so sure really what about it you were trying to ask me. You can always lift up your hand and let me know. I will answer accordingly. Okay, 2 people raised their hands quickly. I want to make sure that I unmute them. Mpo, you want to say something? Go ahead. I'm going to give an opportunity. Sean, you can mute yourself, or rather let me mute you. And then after that, CM is coming. Mpo.
Okay, hello, sir. So
Hi.
I just wanted to ask, what happens when you didn't use work energy theorem formula specifically and you used another method to get the same answer?
It will be fine. That's okay. It will be very much okay, right? If you were to notice in the memos, you'll notice that there are many ways of doing this, many different ways. And I'm not going to spend our time showing you way number 1, way number 2, and way number 3. I'll pick the one that I think is pretty much straightforward, is easy to understand for most of you, but you can also use another method and still you get the same answer. There are many ways of doing this. Thank you so much, Paul, for that one. Let's take it up from there. Let me go to CM. I can't see CM Khota, so you got your hand up. Okay, CM, there you are. I'm gonna lower the hand. I wanna move to my next question, guys, as quickly as possible, but let's keep working.
Morning,
CM.
sir.
Hi, how are you?
Can you hear me? I
Loud and
actually
clear.
wanted to ask. I actually wanted to ask the same question, whereby I did not use work energy
Oh, okay.
theory. I
All
used
right, no, that's
F net
fine.
is equal to. Okay.
Okay, that's okay. Good one. I've already unmuted Huta, so go ahead. I'm waiting for your question to come through. There you are.
Yes, so I wanted to ask why on the mass of the gravity, why do you have 1,680 while the bucket of the mass is 80 kg?
Exactly. It's because the water is inside the bucket. And so the mass of the object is inclusive of the mass of the bucket and mass of the water. 1,600 plus 80 gives you 1,680. So you must be able to include that.
Okay, thank you.
Thank you. Much welcome. Much appreciated. All right, I think someone else has a hand up. Guys, woo, it's crazy out here. Neliswa, go ahead, Nelisa. I'm going to unmute you quickly. I want to move on to my next question. Please make sure that you've written this quickly. Nelisa, probably with the last one. Then I move on to my next very interesting question. Go ahead, Nelisa.
Hi, sir. Can you hear me?
Loud and clear.
Well, I'm getting a negative 32,980 on work of gravity. I don't know if I'm the wrong one.
Okay, the work of the gravity, which is this one here, right? I haven't done, you know what I did? I just did the answers straight up. So someone can confirm if the number that you just said is what it is, right? For most of you guys, and I understand, it's a calculator error. I do understand sometimes. So just work on it. If you work on it properly, remember, Nelly, so you're looking for WF, you're not looking for work done by gravity, you're looking for work done by friction, right?
Yes.
And then Ukabelo just sent a message to say, Nelly, so you're correct for the work done by gravity there. Everyone says, I think even Paul confirms that. Thank you so much, guys. I see that. So here in this case, you get this number, get that number, but you are looking for work done by the friction. And I'm going to take this out now and move on to my next question. All right, here's my next question right here. This question is very interesting. It's a 2019 Limpopo paper prelim. Please write down the title. 2019 Limpopo paper 1, question 5, as you can see. I'm going to start on it right now. So allow me to move very quickly on this particular one. Question 5, please write down the title and we're learning. A 150,000 kg rocket is launched, bold letters, from rest. The rocket motor generates a thrust of 4,0 times 10 to the power 6 newtons. Thrust, that's a force, okay? So when the rocket motor is eventually moving the rocket, the thrust is the number given right there. The mass of the rocket were given, and also we are told that it is from rest. For me, that's critical. So the initial velocity of this particular rocket should be 0 from rest. And then in this case, they say ignore the effects of air resistance and any mass loss. So remember, in the previous question, we couldn't ignore friction. They told us consider it. This time, we're ignoring it. That's great. 5,1, definition. Define the term conservative force. I think we said it in the other question that we did in the beginning. But again, let's reiterate. It is a force whose work done is path independent. I suggest you rewrite it. The more you rewrite something, the more you learn about it, okay? So it says conservative force, a force whose work done is path independent. A force whose work done is path independent. And just as a heads up again, family, let's get things clear here. As a heads up, we need to be able to define and give examples, right? We need to be able to define examples of define a conservative force, give examples. Define a non-conservative force, give examples. That's critical for me. Here's 5.2. 5.2, classify air resistance as a conservative force or a non-conservative force. You see, this is so important. If you didn't know air resistance and what type of force it is, you can't be able to answer this. This is why it's important to know the definition of the type of force and the example of that force. So in this case, air resistance is actually a non-conservative force. Someone will ask me, why? It's because air resistance is a force whose work done is path dependent. Because that's how you define non-conservative forces. So air resistance, good example of a non-conservative force. Great one. 5,3. Draw a labeled, so 5,2, non-conservative. Draw a labeled free body diagram for the rocket while it is in motion. All right. There's my dot, free body for the rocket while it's in motion. When the rocket is moving up, there is the force of thrust. So I'll just write it as thrust because that's how they put it across. Generates a thrust right there. And obviously, there is the most common force that we love, the force of gravity or the weight. Please do remember they said ignore the effects of air resistance and any mass losses. So for 2 marks, that becomes your free body diagram, the dot. Again, guys, just so you may know, remember, if you were asked to draw the force, not free body, force diagram, then instead of drawing the dot here, you would put something like a box kind of thing, yeah, and then you put thrust there, and then you put your force of gravity or your weight. You can call it force of gravity or weight. So the only difference between the free body dot, the force diagram box. So be very careful as to what they actually ask you, right? So somebody's asking, so what is thrust? Thrust is a force, right? It's the reason why the rocket goes up. Collectively it's called a thrust, right? If we were to use colloquial English, we'd say it's a push, push, push. That's probably what we would say. But it's a thrust right there. Nelisa, got your hand up. I'm unmuting you. Go ahead.
Sir, can you hear me?
Loud and clear.
Okay, sir, I'm sorry, I have to take you back to conservative force. So I'm asking, what does it mean? What do they mean when they say a force for which work done in moving an object is independent on the part taken? So I want to make sure I choose the right forces for a conservative or a non-conservative. Like, I don't understand when they say independent and dependent on the part taken.
So you're saying you want to know what the actual definition of conservative means and all that. Okay, let me try and clarify the best way possible. Let me give an example of a conservative force. I'm going to start on that one, conservative force, so that you may know which one I'm going to be dealing with in essence. Force of gravity. You can mute yourself in the meantime. Okay, Van, just keep yourself unmuted so that in case you still don't understand, we can have a bit of a conversation. Right, all right, Tilwe, yes, you're right. You can write it as FA thrust. That's fine. I'm okay with that. When an object is going up, the force of gravity acts down. When an object is going down, the force of gravity acts down. So I'm learning that the force of gravity maintains its direction regardless of whether the object is going up or down. Whether you go up, I will act down on you. That's force of gravity. Whether you go down, I will act down on you. That's force of gravity. So the force of gravity maintains its particular direction regardless of the motion of the object up or downwards. That's point number one. Point number two. Now, the work done by the force of gravity will not be affected by how far the object went. So in other words, the object can go up 100 meters, go down 2,000 meters. The work done by the force of gravity is independent of the actual path taken by the object. Hence, when you're defining a conservative force, like force of gravity, you will define it as a force whose work done is path independent. It does not matter how far and where. Listen to my two words, how far and the direction of movement of that particular object. The work done by a conservative force will be the same, whether the object went up 200 meters or went down 50,000 meters. The work done by a conservative force is path independent. That's what I mean. Are you okay with that?
Yes, I'm okay with that. Thank you, sir. I understand.
Beautiful. You can mute yourself. Let me go to my next question. 5.4, state in words, the work kinetic energy theorem. State in words, the work kinetic energy theorem. Here we go. So it says the net work done on an object is equal to the change in its kinetic energy. The net work done on an object is equal to the change in its kinetic energy. Please write that one down. Super important. I'm going to my next one, which is a calculation. 4 marks on the bag. Let's break it down. What are we saying? 4 marks on the bag, right? Okay, I'm getting a question here from the chat here, and I don't get that. I don't understand what's going on. right? Pearl is saying when don't you ignore, I don't get that. I think I'm saying when do I ignore FF? When they say to me, ignore the effects of air resistance. Air resistance, definitely that aligns to FF. So when they say that, definitely I ignore it, right? That's basically what I want you to know, right? And then Paul says on the previous questions, we didn't ignore the air resistance. So air resistance is like resisting the motion of the object. Is it friction force? Yes, please. Yeah, that's what it is, right? Air resistance. I don't know if you guys have seen this. When it's windy, like when it's really, really windy, and you're trying to move, right? You're moving against the air. So there's a bit of some resistance right there. And the air resistance is acting opposite to your movement. Like it's July right now, so there's lots of wind that will be coming through probably. And so when you're moving against the motion of the wind. Air resistance, pretty much aligning to friction as it were. 5,5, we go as a team. I like to move through well. 5,5, use the theorem in question 5,4 above to calculate the speed of the rocket at a height of 500 meters. Okay, so the theorem, what does it say? Right, it says work net is equal to change in kinetic energy. That's work net. And I'm saying use the theorem in question 5,4 to calculate the speed of the rocket at a height of 500 meters. So let me see who's doing work on the object. According to 5.3, where we dealt with the free body diagram, the guys that are ultimately doing work is the work done by the thrust, right? Let me just put it as T, thrust, plus the work done by gravity as it were. All this is equal to change in kinetic energy, half mv f squared minus half mvi squared. That's okay. Work done by the thrust is the force of the thrust, right? And then multiplied, okay, by delta y. Remember, guys, it's vertical, multiplied by cos theta, plus the work done by gravity. And I think we made it clear that it's going to be Fg, which we now know is mg, okay? Fg, right? Delta y, then cos theta. Let me do a bit of some maths here. Now, the mass of the object is the same. So I can factor out half m, mathematically speaking, half m bracket vf squared minus vi squared. So that should be okay for me. Okay, let's keep working on this. Now, obviously, the force of the thrust were given, I think it's 4 by 10 to the power 6. How far did we go? Delta y is 500 meters multiplied by cos 0. Why cos 0? Because the thrust is moving in the same direction as the displacement. That's fine. Plus mg, which is Fg. Mass of this particular rocket, 150,000 multiplied by g, 9,8 multiplied by cos. Guess what? The force of gravity is acting downwards, Fg multiplied by cos 180. All this is equal to half mass of the object, 150,000 bracket Vf squared, which I don't know, which I'm looking for, because it says calculate the speed of the rocket at a height of 500, minus my initial velocity, it was 0. 0 squared. Where do I get that confidence? From rest. And so because of that, I can actually come up with my answer. Remember, guys, I'm looking for VF. I'm not going to do all the maths for you. The VF, you can calculate it later on, is 129,87 meters per second. Sounds pretty fast, and that's pretty much okay, especially when you consider that you're dealing with the rocket. 129,87 meters per second. All right, write that one down. Let's see if we can move on to something else, something a bit more interesting. So basically speaking, this is what you're going to be getting on vertical objects, vertical, up, down, vertical objects. all that. So you must be able to draw the free body diagram. I cannot, for the life of me, overemphasize how important the free body diagram is. Without the free body diagram, we are nothing. The free body diagram is our go-to diagram. With it, we can be able to find what cos theta is. With it, we can be able to know which force is positive, which force does negative work, all those kind of things right there. Write this one down, family. I want to move on to my next one. Gravity is definitely 9.8 Pearl. G is 9.8. Remember, FG is mg. mg. So where there's FG here, I put m and then also g. 9.8 is each way. All right, somebody's asking to me, where's the change in the velocity say? Obviously, change in velocity, the object was here, and then it went up there. So its initial velocity, all right, no, change in displacement rather. Its initial displacement was 0. Then its final displacement right here, where they want us, is 500. So the change in the particular displacement is 500. Its final displacement, 500, minus initial displacement, 0. Family, displacement has to do with the concept of a change in the position. That's displacement, right? Right, somebody says the work done by gravity, did I forget it? I did not forget it. There, this is the one, WG, which eventually is stood for by this, which eventually becomes this. Follow my lead all the time. Work done by T, work done by gravity is each way. Please write this down, guys. That's your answer, is each way. Okay, guys. Somebody just unmute themselves and let me know what question they have, because when you write questions on the chat, I can't really fully understand what you're saying to me. Sebenzile, go ahead. Sebenzile, I've unmuted you. Okay, let me try that again. CM, in the meantime, while we wait for Sebenzile, go ahead, CM.
Sir, I'm getting confused on the displacement. Like, I get you said FG times displacement. So I was asking what happened to that displacement? Is it 9.8?
Okay, I think people, okay, now I understand where people are coming from. 1,500 mg,
Times,
okay, the
yes.
delta x, okay, that 500. Now I see where my mistake was. Okay, that's why I needed you guys to unmute yourself there. So the 500 right there. So I think I put it in formula version, but I missed one number right there. Okay, that's okay. Thank you for that one. 129.87. That's okay by me. Let's see if we can move on to something else on this question. Thank you so much. I think CM has spoken for everyone, which is good. Okay, I move on to my next question, family. Let's go. Here's my next question. This one is a 2016 March paper, and it's paper 1, question 5. Please mark that one there or write it down. 2016 March. Thank you guys for the many helps that you're giving us here. We really appreciate and all. Guys, can you also recheck your answers? I don't want us to have a math session in a physics lesson. So in case you want to recheck your answers in comparison to mine, you can do that later on. I should be able to send you the memo for this as well. But yeah, basically speaking, we'll cover up everything. And so you guys can pretty much take it up from there. The diagram for this question is the one at the top right corner. Please look at it right there. That's very important. At the top right corner. If you can't see it nicely, just increase the brightness of your phone or the brightness of your laptop. But here's the question. A constant force F applied at an angle of 20 degrees above the horizontal pulls a crate or pulls a 200 kg block over a distance of 3 meters on a rough horizontal floor as shown in the diagram. Just so we may know, the terminology should lead us to something that we understand. The word rough simplifies to me that there is friction, rough horizontal floor. So let's get this right. The object is on a horizontal surface. It's not on an incline. The object is not dangling anywhere. It is on a horizontal surface. The coefficient of kinetic friction, mu k, between, so that's how you write it. It's not uk, it's mu, it's a Greek word. Mu k between the floor surface and the block is 0,2. So that's the coefficient of kinetic friction. Fine. 5,1, give a reason why the coefficient of kinetic friction has no units. I need to specify. You see, this part of what we're talking about right now speaks again to issues to do with the topic application to Newton's laws, right? So in this case, I want you guys to get this right. The coefficient of kinetic friction does not have units because it is a ratio of forces. Let me explain. If you were to work with me, I will tell you that the force of friction has a formula. It's mu k multiplied by normal force. That if asked to get friction, please use this. Mu k multiplied by normal force. So the force of kinetic friction, let me be specific. Force of kinetic friction, Fk, is mu kn. So if I was to make mu k the subject of the formula, it was going to be Fk, all right, right there, over normal force, which is mu k. Now notice the following. Force of kinetic friction is measured in newtons. Normal force is measured in newtons. Newtons cancel, newtons cancel. So the units are not available. So for the coefficient of kinetic friction, it has no units. Why? Because it's a ratio of forces. That's your answer. It's because it is a ratio of two forces. Maybe just specify that one. Because it is a ratio of two forces. Very important that you get that right. Can I just work out something quickly here, family, just in case it comes out in other examples before I go to 5,2. Listen up, listen up. The kinetic frictional force on a horizontal surface is given by this formula. On a horizontal surface is actually mu k mg, if you want to put it across nicely, because normal force has the same formula as force of gravity, which is basically mg. So on a horizontal surface, horizontal surface, the formula for kinetic frictional force is actually equal to mu k mg. On an incline, oh, listen to this one. On an incline, the force of kinetic friction is mu k n, right? That's okay. But I get this right. I want to get this right. Cos theta on an incline. On an incline, the kinetic frictional force is mu k n, but then there's cos theta, where theta is the angle of inclination. Very important that you get this right. So on a horizontal surface, this one eventually getting to that. On an incline, this one right there, which eventually, guess what, gets up to this particular situation. And again, as always, theta is the angle of inclination. That's what theta is, the angle of inclination for cos in this particular formula for kinetic frictional force. I'm ready for my next one. So that was just me putting on my side notes so that you can remember this in the exam as you're going along. State the work energy theorem in words. Oh, we love this, and maybe we're tired of this, but eventually it helps us to understand quite a lot. Here's our answer. The net work done on an object is equal to the change in the kinetic energy of the object. We must sing this particular definitions. The net work done on an object is equal to the change in the object's kinetic energy, right? Okay, Kulani says to me, Sean says to us here, what if, say, you wrote it as, because it's a ratio of two forces, the forces being frictional force and normal force. That's still okay. Even if you end it up as saying a ratio of two forces, that's still pretty much fine, right? You don't actually need to specify which forces they are, because once I hear the word or the phrase ratio of two forces, then for me as a marker, I'll be able to say, oh, so forces cancel out, ratio, forces cancel out, not newtons, so that's why it doesn't have units. 5.3, draw a free body diagram indicating all the forces acting on the block while it is being pulled. All right, eyes on, okay, I want to say eyes on me. All right, let's go. All right, listen to me. Let's work it out. Yo, I'm used to the classroom setting, eyes on me. Right, listen to me. The object is on a horizontal surface. Listen to my English. The object is on a horizontal surface, sure. But the force applied to the object pulling the object is acting at an incline. I never said that the object is on an incline. No, I did not say that. I said to you, the object is on a horizontal surface. What is on an incline in this case is what is acting at an angle, rather, in this case, is the force acting on the object, the one responsible for pulling it. So I want to draw the free body, 5.3. I want to draw my free body on 5.3. Here's what I'm going to do. I need a dot, definitely need a dot. There's my dot right there. So let me talk about what I know. The object is moving. As you can see, it will be moving to the left. So I have my resident evil guy here. Force of friction, always there to disturb our lives. I got the normal guys, the cousins. Force of gravity, object is on a horizontal surface, dot, free body. Then I've got my normal force. Force of gravity and normal are the same. Talk to me about the force F. The force F is acting at a certain angle, and I'll call this angle F, so this force F right there. And I'm just going to put a dot here because I need to show this to you on my next question, and I'll put angle 20 there. That should be okay. But can I just say this quickly, family? Even if you are going to leave it like this, it's still fine. For me, as the examiner or the marker, I can see that the student understands that the force that is pulling the object is pulling it from a certain angle. Hence, the arrow is not horizontal, but rather the arrow is inclined. So this will be okay. That will be fine for me. So write this down. Very important that you get that right. 5.3. Let's try 5.4. Let's try 5.4. Oh, 5.4 is interesting. So there is 4 marks here. There is 4 forces right there on the previous one. 5.4. Show that the work done by the kinetic frictional force, WFK, on the block can be written like that, and that's 4 marks. Okay, let's get down to learning a couple of things. Now, when the force is acting at an incline, we need to understand a couple of interesting things, right? When a force is acting on an incline, that force is divided into components. There is the X component, which is acting on the horizontal path, and there is the Y component, which is acting on the vertical path. So a force that acts at an angle can be broken down into its particular components. If I was to draw them, the vertical component in this case will be Fy and is upward, just drawing it like that. The horizontal component in this case, I'll call it Fx. So I've kind of like created a right angle triangle. And so because I've created a right angle triangle, I must speak trigonometry. Now in trigonometry, the right angle triangle, let's go to a bit of some math. The right angle triangle can be broken, or rather can use the ratios of sine, cos, and tan. So let me see what's going on here. Let me see what's happening. If I consider 20 degrees, then Fy is opposite and F would be hypotenuse. Opposite, hypotenuse. So if I did the math, I would say sine 20 is opposite Fy over hypotenuse F. And so when I break it down and make Fy the subset of the formula, Fy becomes F sine 20. This is super important. Fy, F sine 20. So the vertical component of this particular force is F sine 20. Vertical. Maybe let's try the horizontal. Fx. Let me do some math. If I consider Fx, then it means to me that Fx would be the adjacent side, and I've got F, the hypotenuse. Adjacent hypotenuse. Sounds to me like cos. So cos 20 is adjacent Fx over hypotenuse F. I can make Fx the subset of the formula. So Fx in this case would be F cos 20. So the horizontal component of your particular force acting at an incline of 20 is F cos 20. The vertical is F sine 20. I want you to write this somewhere because now I'm going to build up to how I get this particular answer for work done by kinetic frictional force. So get this to write this down on the side, how you break this down. So the vertical component is always having the sine in it, and the horizontal component is always having the cos in it. Just maybe remember it from that particular level. Vertical component, the sine in it, the horizontal component, the cos in it. I'm taking this out. I want to calculate or show that work done by kinetic frictional force is that. I'm taking this out, family. Here it goes. Let's go back to our free body. In our free body, with a situation like this, and you guys must have seen like this and like that. So I'm not going to draw any of the horizontal forces because my point is on the vertical ones. So on the vertical forces, you've got this one, Fy, and then you've got the cousin normal force, and then you've got this other big brother force of gravity. Usually, if the applied force is horizontal and the normal and the gravity are perpendicular as always, we always say the normal and the gravity force are equal in magnitude, just basically opposite in direction. That's what we normally say. But if you look at the scenario, you've got the normal force acting upwards. You've got the force Y also acting upwards. Suddenly, we've got two forces on an upward trajectory. They are acting upwards. Which force is normal? Which force is Fy? Now, all vertical forces in the context of work energy and power, particularly in this question, these vertical forces must be balanced. The upward vertical forces balanced, the downward vertical forces balancing with the upward. So let me translate my English into physics. Let me speak the English first. What's my English? I'm saying to you, the normal force, okay, the force Y, okay, both of them are acting upwards. Sharp. The Fg is acting downward. Okay. The Fn and Fy are upward forces, which then, if you add them, Fn plus Fy, these upward forces to balance, they must equate to Fg, the downward vertical forces. If you go back to work energy and power again, you would understand that the vertical forces, they do no work on the object. Why is it that they do no work? It's because they act perpendicular to the displacement of the object. Oh, I gotta repeat that. Fn, Fy, Fg, they do zero work. Why? They act perpendicular to the displacement. So then what are you saying to us, say, when you're telling us that there must be balance? This is what I'm saying. This is what I'm saying. Right, this is what I'm saying. Okay, follow my lead. I am simply saying to you, if you were to say Fy, all right, plus Fn, okay, you will get Fg. The vertical upward forces must balance the vertical downward force. Fy plus Fy plus Fn will equate me to Fg. This is interesting. So hold on. Tina say we're looking for the work done by friction. Yes, that's what we're doing. So what is the work done by friction? The work done by friction, right, will be equal to the force of friction delta x cos theta. That's always the work done by friction. But frictional force, and I made it clear to you earlier on, frictional force has a formula. The formula for friction is mu k n. And this is friction on a horizontal surface. I didn't say on an incline. So Ff is mu k n, where n is the normal force. And because we're dealing with work delta x cos theta, I want you to get this. See where I'm building my idea. Normal force, I don't know it. But from what I've just extrapolated here, the normal force Fn, right, can be written as Fg minus Fy. Earlier on, right now, I said Fy is F sine 20. That was me. That was Fy. F sine 20. So the normal force, Fn, or you can even write it as N, capital letter N, normal force. I put it as N. The normal force is Fg minus F sine 20. Okay, let's bring this here. Work done by friction, kinetic friction, is force of kinetic friction, right? Which is Ff, I will write it as Fk, doesn't really matter. Fk delta x cos theta. So what is Fk? Mu k n. Who's n? Normal force. Do I know normal force? Yes, I just found it. It's Fg F sine 20. Bring it up. Let's work. Mu k, okay? N, who is n? Fg minus F sine 20. Delta x, okay, multiplied by cos theta. That's what I have. Remember, I'm trying to make it look like this. So far, the work done by the kinetic friction is mu k f bracket Fg minus F sine 20 delta x cos 20. So far. But hold on. Fg has a formula. Which one? Say mg. I'm still using letters. I haven't put numbers. So mg minus F sine 20 delta x cos theta. Let's put numbers. Let's put numbers together as a team. Let's put numbers. So mu k, I'm given 0.2. Oh, beautiful. Mu k, 0.2. So I'm going to mu k now, and let me just bring it up here where there's a bit of more space. Hold on, let me just pull through like this. So I'm going to just bring this whole thing here that I have so far. We've gone from that part to that part. I'm going to move this to this side here, or rather write it from here. So I'm moving it here like that. Okay. So now mu k 0.2 bracket m, mass of that particular object, and what is the mass of the block? 200. We're doing maths. Multiplied by g, there I am, 9.8, minus f, which I don't know at all, multiplied by sine 20, and sine 20 is a number, by the way, multiplied by delta x. How far did we go? 3 meters. Multiplied by 3, multiplied by cos 180. Why? It's because force of friction always opposes the displacement of the object. If you were to play around with the maths in total, these are numbers, your answer becomes exactly negative 1176 plus 0.205 F. Exactly how they gave me right there. I'm waiting for questions. Talk to me. Talk to me. That's what you do. That's exactly what you do in this question. You're looking for the work done by kinetic friction. You needed to know the influence that vertical forces Fy, Fn, and Fg are to one another. They are equal but opposite. The top upward Fn and Fy added together will give you Fg. Make Fn the subject of the formula. Keep in mind that friction is actually mu k n. Kinetic friction, mu k n. Whose normal force? You've made it the subject of the formula. The rest is just mathematics. Don't forget that theta, the angle of theta 180, the angle between the force vector and the displacement is always 180 as each way. Remember, guys, when you want to write this down, you can always zoom in, zoom out your phone, device, whatever the case could be. Are we okay on that? Okay, right. Right, we're still good. Write this down as each way. If there's any question whatsoever, got your back, you will let me know. Let's keep working. The more we do, the more we know. 5,5, I'm going, let me give you a further, maybe 45 seconds to finish this one up here. A further 45 seconds to finish this one up here. Ten more seconds. Okay, I am taking this out. Here it goes. Gone, gone, going. Right, beautiful. You let me know again if there's something that you didn't understand and all that. Okay, we're quite a number of people. We're almost 100 people on this platform. So you guys can ask me as many questions as possible. Please do not be afraid of asking questions. Remember, you need to learn, which for me is the most important thing. 5,5, 4 marks again. Calculate the magnitude of the force F that has to be applied so that the net work done by all the forces on the block is 0. Okay, so they're saying calculate the magnitude of F, okay, that has to be applied because F is an applied force anyway, though it's applied at an angle of 20 degrees to the horizontal. But we need to calculate the magnitude of the force F that has to be applied so that the net work done by all forces on the block is actually 0. That's what we need to calculate. Let's start working on 5,5. So obviously from what we're getting here, we are clear that the net work should be equal to 0. So that's fine. They actually told us that. The net work from the free body diagram is the work done by these particular forces. The work done by the applied force, but please guys, keep in mind is this one. Look at this. Obviously you've got the normal force and you've got this incline, and then there's force Y, and then there's force X right there. Then there's force of friction, which is okay. And then also on the flip side of the coin, there's force of gravity. We are clear that the guys doing work is force of friction, I agree, is doing work on the object. Force X is also doing work on the object. The ones not doing work on the object is force Y, force N, force G. Why? Because they act perpendicular to the displacement of the object. So their work done is actually 0. Theta is 90, cos 90 is 0. So that's a very important thing to remember. Vertical forces do no work on the object because they act perpendicular to the displacement. So the only two guys doing any significant work is the force X, and force F as well. But check this out. I need a bit of something. Zandile, I see your hand. I'll attend to you right now. So what is the work done by force X, the horizontal component of F? Obviously, it's force X, all right, which is delta X cos theta. The work done by friction, FF delta X again cos theta. These works added together must give you 0 as the question specified. Remember what I said about Fx earlier on when I was trying to explain to you. I said to you, Fx is equal to F cos 20. That was FF for us in the previous 2 questions. So where there's Fx, I put F cos 20. So that becomes F cos 20. Remember, I don't know F. So that's F cos 20 multiplied by delta X, which for me in this case, the delta X I think should be equal to, I think it's 3 multiplied by cos. Check this out. From the free body diagram, the Fx, just pause it there. The Fx is in the same direction as the displacement. So then the theta of them is 0. So for that one there, I put theta as 0 plus FF, right? Now we don't know FF, we just don't know this whole thing, actually. Okay, we do know this and we will know this. But did you remember that in the previous question, we actually found the work done by Fk, force of kinetic friction, work done by friction, like that. We found it. We found it as this version. So I can write it like that. I can write it as negative 1176 plus 0,205 F. All this is equal to 0. If you are with me in a math class, I will tell you that here, this is actually F. There's another F right there. Imagine if this was like math, X. For example, let's say 2X plus negative 3X, like that, and all. So remember, all you're looking for is F. So the mathematics of it is pretty much straightforward. Get an answer for me. Let me see if I can do it with you on this one here. Obviously, cos 20, I can get it as an answer, multiplied by 3, multiplied by cos 0. Let me see what I get. So for me, and I'll round it up here, I got an answer like 2,82F. Remember, there's that F there. So this whole number here is 2,82. Then it was a plus. Then remember, it's the minus there on the outside, minus 1176 right there. Then plus 0,205. 05, then 0.5 F. I'm looking for F is equal to 0. I think mathematically, I can jump this guy to the other side, transpose it, 1176. Then these are like terms, these two, okay? Right, so these are like terms. You let me know if I made any mistake, but let's just do the calculation together and see. 2,82 plus 0,205 F of that. So I think I get a number like 3,025 F. Remember, by the way, all I'm looking for is F. So let me see if I can divide that number by UF. And yes, I can by 3,025. So I get my F as 388, I think it's 76 newtons. I rounded it off quickly because I didn't want to write all the numbers. But if you don't round it off, I think you should get a number like 388,88 newtons. So I suggest you don't round it off. This whole F cos 20, blah, blah. Take the number as it is, added together, so you get the most accurate of answers. I've got 2 hands that are up right now. So my first F is that one. 2 hands are up already. Great. Let me start off with Uzandile, and I'm going to go to the next one. Let's go. Uzandile.
So it's actually okay. I got it while you were still explaining.
Okay. All right. That's good, Zandile. That's fine.
Thank you.
All right. Thank you. Let's have the next person. Let me just look for the next person. Who's that? Sebenzile, go ahead.
Sir, can you hear me?
Loud and clear.
Oh, so I got confused. Can we go back to the blue part?
The blue part.
Yeah,
Yeah.
yes. we said, are we representing the negative 176? Are we representing that as FF?
No, we're representing that as work done by FF. That's what it is there. Because we already know it. Okay, maybe what could help you is this. Let me just take this out, right?
Okay.
And keep it as WF. Then remember that WF is this particular number.
It's this thing. Okay,
Exactly.
thank you, sir.
Like
Now I
right there. It's not
understand.
FF. Yeah, good one. Thank you so much for that one. Much appreciated. Write this down, family. Let me move on to my next one. I'm actually getting a feeling that I want to give you a question. Yazin, I want to give you a question, but let me just do one more and see if it makes sense for me to give you a question to try on your own as we are learning about all of this, right? Somebody says, can we do a question similar to question 5.4? That's, let me see who that is. I don't know if I do have one, Nicole, but I'll see how far it goes. I don't think I have one here with me, but maybe in the WhatsApp groups, I'll send one. I'll look for one maybe tomorrow or day after tomorrow, because I'm very busy, and then I will see what can happen on that. Okay, let me take this out. We are moving through. It will also help you guys listen up. If you were to subscribe to my YouTube channel, you should be able to get quite a lot of information from that particular YouTube channel. Very, very, very insightful. Remember, I do both maths and physical science for grade 12. So you can go check out the videos right there. You can watch me, rewind me, delete me, whatever, download me, upload me, wherever you want. That's all up to your discretion right there. Okay, I'm ready for my next question. And this question is 2014 Free State Prelim, paper 1, question 5. I picked these questions intentionally because to me, they mean quite a lot and can help us to understand things. Here we go. 2014 Free State Prelim, paper 1, question 5. A 3 kg metal block moves from rest at point A down an incline as shown in the diagram below and reaches a speed of 6 meters per second at point B. Section AB of the path is frictionless. All right. Then it says on 5.1, would you describe the movement of the block on section AB of the path as free fall? Give a reason for your answer. So maybe we need to understand what free fall is. This is connotations of the topic, vertical projectile motion. Free fall is the motion of an object where the only force acting upon it is the force due to gravity, or the only force acting upon it is gravitational force. So an object is said to be at free fall when the only significant force acting on that object is the force due to gravity. Sharp. A to B has no friction, frictionless. Would I describe section AB of the path as free fall? My answer is yes. And I want to give a reason. Yes, because between A and B, there is no other force acting on the object except force due to gravity. So between A and B, there is no other force acting on the object except the force due to gravity. So my answer for 5.1 is yes, right? Yes, comma, no other force acts on the object other than gravitational force. Yes, comma, no other force acts on the object other than gravitational force, right? Gravitational force is it way. That's a beautiful one. So I would describe that as it way. But let's work it out on the next one. 5.2. Calculate the net work done on the block as it moves down section AB of the path. I'll check the messages later, guys. Let me just finish this up quickly. Calculate the network down on the block as it moves down section AB of the path. All right, let's work it out. Follow my lead. Let's break it out from there. The network is equal to delta K. That's what we've known. So what are we given about this situation? I know the velocity initial here, 0. I know the velocity at point B, 6. So there was a change in the velocity. The network is half mvf squared minus half mvi squared. So then in essence then, it's going to be half the mass of the object 3, the final velocity of the object, I think it's 6 squared, minus a half mass of the object 3, initial velocity of the object 0. The object was at rest. You guys must have seen that. Great. So the network, which is equal to change in kinetic energy, eventually it means to me it will be about 54 joules. Let me just do a heads up, family. Listen to me very carefully. Whenever between two positions, there's a change in the velocity. Just know that a change in velocity ultimately brings a change in the kinetic energy. After all, kinetic energy half mvf squared minus vi. So the vf and the vi are different, hence the change in velocity, which brings rise to change in kinetic energy. And by contrast and comparison, the change in kinetic energy is equal to the work net. So 5,2, your answer is 54 joules. Let's try 5,3. 5,3, quickly on that one. I'll attend to the messages. Allow me to move through. Allow me to move through. Right? Okay, somebody's asking, okay, how about the force of normal force and all that? But guys, okay, remember this, the normal force, which probably acts upwards, and then force of gravity perpendicular. These two guys, eventually, they do nothing. They act opposite and equal. So the guy who's actually doing anything significant here is the force of gravity. Hence, I've got the confidence to say it's free fall, because the only force that acts on the object and does work on it is the force of gravity. Normal, gravity perpendicular, because I'm on an incline, they give me 0 work. They act on the object but do nothing to it. Remember, I'm looking for a significant force, and therefore you can call it a free fall. Okay, thank you for those questions, family. You guys are doing wonderful work. Let me try and see if I can go to my next one quickly. 54 joules and all. Here we go. I'm on my next question. It says to me on 5.3, calculate the height of the block at position B, and that's 4 marks. The height of the block at position B, so the height of the block right here at this particular position B. Let me just show you what the logic is here. The height of the block at position A, maybe from the ground, right, would be basically about position A from the ground would be about 7 meters, 6 plus the 1 right there. So the height of the block at position B would just be this height, maybe from there to there. And for now, I really don't know what it is. I honestly don't know what it is. So I don't know this height at all. Fine. But how do I get this right? Now, according to the conservation of mechanical energy, the conservation of mechanical energy states that in an isolated system, the total mechanical energy is conserved. What is an isolated system? It's a system whereby the frictional force is unavailable. So between path A and B, I can safely say to you the mechanical energy is conserved. Where do I get that confidence? It's because it's a frictionless, that's what they said, frictionless surface, part A and B. So the mechanical energy, EMAC, at position A, and the mechanical energy, EMAC, at position B, they are equal, they are conserved because the system is isolated. Mechanical energy has a formula. Mechanical energy is the sum of the kinetic energy and the potential energy. So when you add kinetic energy and add potential energy, you're going to get your mechanical energy is equal to the one at A, much as it's equal to the one at B, because there is no friction, it's conserved. That's all about EMAC at A. EK at A is a half mass of that particular object. As you can see, the object is 3. What's the initial velocity at A? 0. It was at rest, half mv squared. EP, mass 3, G 9,8 multiplied by the height right there. And the height is 6 meters. See, I want to show you how I use 6 meters, right? You see, I'm gonna use 6 meters because you know why? I need this part here. So I'm gonna find out from there to there. I'm gonna use 6. Then I'm gonna show you how it actually makes sense. The mechanical energy at A is 6, because from there to there, I'm at 6, right? So let's work it out from there to there, because I'm gonna use this part at B. Listen to me carefully. Let me put 6. I'll make it clear to you how 6 makes sense. So that's 6 right here. Is equal to EK, the kinetic energy, which is a half mass of the object, that's multiplied by 3, multiplied by the velocity at B, 6, I think it's 6 squared, all right? I think so. Yes, it should be 6 squared. There it is, velocity at B, 6, plus EP, which for me is mass of the object, 3, multiplied by 9,8, multiplied by H. And when you get your H is 4,16 meters there. Let me show you. So the total height from this position to that position is 4,16. Exactly that. 4,16, the height from the ground to position B right here. Now, somebody's saying to me, okay, so why didn't we use 7? So why are we using 6 and not basically 7? Right? I'll show you, especially on the next question, why this 4,16 is super important for me. Why it's super, super important. Because in essence, if I wanted to find the height from here, let me use a different color, but let me use green. Look at this, guys. If I want to find the height from UP to this dotted line, all I need to say is 4,16 minus 1. That's all I need to say. 4,16 minus 1, which is 3,16. So from here to the dotted line, 3,16. From the dotted line to the ground is 1 meters. Add them together, they ultimately give you 4,16. So in essence, therefore, the height of this object from the ground is 4,16. Remember, I was using the mass of the object here and the height of the object at A and the mass of the object there and the height of the object also at B right there. So you guys want to get that right and pull through. Write this down. Let me see if I can do it another way. Write this down. Let me see if I can do it another way. Write this down quickly. There should be another way I can do this. Okay, I think I went to the wrong slide. I've stopped sharing quickly. Hold on. I want to go back to that one. Okay, those that were still writing, let me just rewrite this another way throughout. So let me write it like this. So it was E K plus E P at position A, EK plus EP at position B. I see your hands, guys. I'm coming through. EK, a half M, mass of the object. I think the mass of the object should be 3. Initial velocity 0 plus mass of the object, which for me is 3g 9,8, and I used 6 deliberately, is equal to EK, that's a half mass 3, velocity at point B, 6 squared, and then plus M, which is basically mass 3, 9,8 multiplied by the height. So the height then here in this case becomes, I think, 4,1. So write this down, guys. I think that's the one that you guys were writing anyway. All right, I'm going to think about another way of doing this quickly. Just going to move on to my next question. Our time is really gone. I'm not really winning because there's something that I want you to try with you guys as well, which is a bit more complicated. But if we can't do it, then I'll make a plan for you guys. All right, let me go to 5.4. I'm going to look for the other way of explaining 5.3 right now. I think, Pearl, you had your hand up. I think a couple of questions there. Let me just round up 5.4 quickly, then I'll come back to 5.3, but write this down now because I can find another way of doing this particular question on 5.3 rather. So I'm taking this out now. That's the height above the ground. Okay, let me go to the next question. Okay, Pearl says she's good now. Thank you, much appreciated. Right, it says here on the next question, just move my annotation here. It says on the next question, on reaching point B, okay, let me be careful about this. On reaching point B, there's point B, right? The block continues to move down the horizontal section BC of the path, which is 5 meters in length. So it looks like from B to C, it's 5 meters. Then it says the block now experiences frictional force. So between B and C, there's friction, and reaches point C at a speed of 2 meters per second. I think for me, at point B, the speed was 6 meters per second. And I just want to make sure that the physics is clear for you guys. When we talk about frictional force, we're talking about a type of force that slows down objects. So it's no surprise that between B and C, your frictional force is acting on the object, reducing its speed from what we have, 6 meters per second, to what we now have as 2 meters per second. So there was a decrease in the speed, a change in the velocity. And eventually, remember, a change in velocity means a change in kinetic energy. So let me go further. Use the principle of conservation of energy. I didn't say mechanical energy, but just conservation of energy, to calculate the magnitude of the frictional force acting on the block as it moves section BC on the path, 5 marks. Dr. Honolo, you got your hand up. I'll come to you now. Let me just finish 5.4. Now listen to me. Use the principle of conservation of energy. Now, there are many ways of doing this. Pick an equation with energy in it. Work net, I love this one, is equal to delta K, right there. Now, who is doing work on this object between B and C? Let me draw my free body diagram. The object goes down. It goes down, and there is no applied force that we're talking about. So force of gravity parallel is acting on the object. There's force of friction also on the object. There is the gravity perpendicular, and then there is the force normal. I just said to you that the normal force and the gravity perpendicular, they do no work. So the guys doing work are the work done by gravity parallel plus the work done by friction, all right? And then all this added together will give me my change in kinetic energy, and I can get it because I've got velocity initial and velocity final. But let's go further. On an incline, we say to ourselves, the force of gravity parallel is actually mg sine theta delta x cos theta on an incline, work done by gravity parallel, plus, and we're going further, work done by friction, ff delta x cos theta. That's what we know. All this is equal to change in kinetic energy. Now, let me work with you. Follow my line of thought. The distance that we got from here to the ground, we got it as 4,16. From the ground to this particular dotted line, where it's level with point C, is 1 meter. So it looks like to me, from point B to the level of point C is 3,16 meters. That's why I'll add 3,16 plus 1, I'll get a total of 4,16. So I want you to see what I'm going to draw here. Look at this. Point C, point B, 5 meters, 3,16. Now, I don't know this angle here, theta, which for me goes with the sine theta. I don't know it. But mathematically speaking, this theta can be found. Sine theta will be opposite 3,16 over hypotenuse, which is 5. So where there is the wall of sine theta, I put 3,16 over 5. That's what I'll put. I want you guys to get my logic here. The distance from B to the ground, 4,16. Fine, 4,16. Then it means that from B to the level where C is 3,16. That's what it is. Because 4,16 is 3,16 plus 1, because this is where the 1 makes a whole lot of sense to me. So from B to the level of C, 3,16. And the theta opposite over hypotenuse, 5 meters. Sine theta, 3,16 over 5. Remember, I'm looking for FF. That's what I'm looking for. So let me do my math. Mass of the object, 3. G, 9,8. Sine theta, I know it is 3,16 over 5. Multiplied by delta x. Delta x is the distance from there to there, which for me again is another 5. Multiplied by cos 0. Somebody saying, Haibo, why cos 0? It's because the object is moving downwards and force of gravity is acting in the same direction as the displacement, 0. Plus FF, which I'm looking for, multiplied by delta x 5. And the force of friction is always acting opposite to the displacement, theta is 180, is equal to delta K. Who and what is delta K? It's a half, mass of the object 3, final velocity of the object right there. For me, I think it's 2 squared minus a half, mass of the object 3, initial velocity of the object 6 squared. So then at the end of the day, all I'm doing is I'm looking for F. And so when I find my FF here, my answer should be 28,18 newtons. Get this right for me. Try to sort it out yourself and let's see if we're winning on that one. Let's see if we are winning on that one. All right, tell me if you get 28,18, just like what I did. And again, if you don't understand something, let me know. But I'm just gonna unmute. Okay, where's the name? I think I've unmuted you. Go ahead.
So can you hear me?
Loud and clear.
I still don't understand why we used 6 meters instead of 7 meters by the previous question.
Okay, for 5.3. All right, it's fine. So, yeah, I'm going to deal with that one there. No problem. Just want you guys to confirm this now. I see where the problem is with you guys. I'll help you out. Don't worry. Others are saying their answer is 2,11 meters. I don't know. Just confirm with me, family. I'm looking for FF, remember. Looking for FF. Can I briefly take this out quickly? Stop sharing quickly as you guys confirm my answer right there. I'm gonna stop sharing as you guys confirm my answer right there. Let me know, do you get 28, yes, somebody saying yes. Let me just get 2 or more confirmations before I become too confident for nothing. Are we getting what others are getting? Oh, lovely. We're winning. We're winning when it comes to that particular question. That's correct. That's fine. And my family members are getting this right. Right, I want to attend to the question that we've been given now quickly. And guys, we're moving. I think our time is gone and all. So there's not much that I can do on all of this. All right, I want to show you something that comes out pretty clear. The other method, and I think for those that I teach at my school, I don't think I've taught you this method, and I want to start new things altogether. Just to answer the question that was given unto me right now, let me just answer it this way. Let me go back to the handout. There we are. I think it's this one. All right, let me just pull this through. On reaching point, no, 5.3, calculate the height of the block at position B. Right, so let me make it like this. At position B, so the height of the block at position B right there. Right, now we only know the object to have moved from position A to position B. Between B and C is 5, that's okay. And then we are not told anything about the distance from position A to position B. We just don't know anything about it. And maybe we don't even need to know anything about it. And so if you were to ultimately do the math, from this position A up to 6 meters right there, and then from this position B up to this position right there at the ground, do me this favor, use 7 instead of 6 and tell me what answer you get. Maybe from there on you can understand what I'm saying. Instead of using 6, use 7. What answer did you get? Write it down for me, I'll wait for you. Instead of using 7, instead of using 6 rather, use 7. What answer did you get? Okay, I'm waiting for you. 5,16. Okay, can I have another confirmation? I need maybe, okay, good. I get 5,16. But when I use 6, I get 4,16, which eventually leads me to my other question, which gives me 3,16. So we are moving from position A to position B. This you can even take this as the level ground if you want it to be. Just the level ground. You can, if you want it to be. So I used 6 to clarify that my position from point A to the ground there will be 4,16. I'm trying my best to try and break it down as to why I actually used 6, right? And you see, if you use 7, you have 5,16. Then when you try to get that 1 meter in the next question, you get it as 4,16 instead of 3,16. Let me see if I can find another question where this logic will come through. But in this case, the only thing I can say, and this is something that I'm really honestly trying to help you to understand, is just from A to this position, 6 meters. Then from B to that position, 4,16. And then from this position here to this point B, 3,16. This one here is 1 meter. I will try to look for another question in the groups where I can play around with it nicely and be able, because I need to move to my other lesson and my time is out now. I will try my best, family, to try and look for another question where I can work from basics so that you can understand why the whole scenario of 6 is used instead of the scenario of 7. So for me, just wait for me. until I get another question where I can explain all of this. I think there's a 2010 question where you use the same concept. I'll look for it and pretty much find it as it were. So allow me to move through on that one. I'm trying my best to make sure that I explain myself, but I feel like I'm not going to be articulate in consideration of time. And also the fact that I think maybe let me use another different question. This could have been a bit of a higher end version of things, right? Right. Let me clarify on that one. Okay, let me stop I'll come through to you. Let me stop the the sharing of the screen and come through to this and talk to you a bit because I need to go now. Right, there's me. Great, that's fine. Okay, guys, thank you so much. You guys have been really wonderful. I will do my part in helping the other guys to understand why I use 6 and all that. Listen up, I need you guys to work extremely hard. The situation that we have in our country is crazy. From the perspective that I'm at, I'm honestly trying my best to make sure that you guys get all that you need. I'm not going to be doing these lessons for free all the time, not at all. It takes a lot of my time and a lot of my effort. I have to do the slides, I have to do everything. So it's pretty much quite intensive. It's a good 3-4 hours and all that, right? So Pearl says you wanted me to do power. I actually started off with power. Did 3 questions that had power in it, right? So I started off with that. You check the YouTube version. Okay, there are other guys that are asking me for other lessons that I do. I do lessons, but most of them are paid for. This particular Wednesday, on the 14th of July, I'm going to be doing electric circuits, part 1, and that's one of your biggest nightmares. And I'm also going to be doing, what's this other one for maths? Euclidean geometry, part 3. So already on part 3 of Euclidean, I'm concentrating on grade 12 theorems, those 3 theorems that come out in grade 12 work. So that's what I'm going to be dealing with. If you're interested in that, all you simply need to do is just DM me or whatever the case could be. And I'm going to put my number here, but I'm going to say it for the Facebook family, 073-974-8498. The Wednesday lessons are paid for. Never, not for free. They're paid for. It's 150 rands for a 2-hour session. They're going to be group sessions like what you have right now. Group sessions as it were. So it's going to be quite a number of you coming through. So if you're interested, please do contact me 073-974-8498. 9 to 11 in the morning, I'm doing Euclidean geometry part 3, grade 12 theorems. Then from 3 to 5 in the afternoon, I'm going to be doing electric circuits, part 1, your biggest nightmares. Thank you. You guys have been wonderful. I'm going to stop the recording now for the sake of our YouTube channel. And then I'm going to stop the recording. There you are.